Okay, in this short video, I'm gonna talk about some fundamental concepts, specifically moving on with the material that we discussed in last class. And the concept here that I want to talk about is multiplication of matrix and vector. So basically multiplication A times X using column space. Now, so this concept, I want to start with an example. Say, consider that if you have a matrix, and I'm going to show you this matrix like 2, 3, 2, 4, 3, 7. This is the matrix, and I'm going to multiply this by a vector x1, x2. How do we perform this operation? So again, first row, first column, that gives me 2x1 plus 3x2. Second row, first column, 2x1 plus 4x2. And third row, first column, 3x1 plus 7x2. So this is the way of performing multiplication. Now, this is known as the dot product or inner product. Or dot product application. There is a slightly different way of looking at this problem. And the way I would write this problem is something like this. I'm going to use, or I'm going to do the multiplication using the columns. So same multiplication, except now I want to write this as 2, 2, 3 multiplied by x1 plus 3, 4, 7 multiplied by x2. And if you were to work out the expansion, you would notice that this expansion is exactly same as the inner product. This is called as outer product. Now, this outer product is of fundamental importance. And what does that mean? It means that we are multiplying each column of this matrix by a scalar, single number, x1. So in outer product, each column gets multiplied by a scalar. In other words, this, and this is an important concept, is taking these two columns, multiplying them by a scalar quantity and adding them. And since it's a linear addition, no squares, no square roots, this is called as the linear combination. So in other words, AX is the linear combinations of columns of X. A times X is a linear combination of columns of A. And this space is nothing but called as the column space. So let me write this down. The combinations of columns fill out the column space of A. Now, here we are trying to think about the matrices as something like a space. Now, let me talk about what do I mean by the space. What do I mean by the space? So if you think about it, let me try to give an example wherein we have just two vectors and say it is given as maybe let's take a very simple example. You have x-axis and you have y-axis. Any point in this xy plane is represented by its x coordinate and its y coordinate. Now, I'm going to write this down in terms of vector space. So think about vector has the direction and a magnitude. And I'm going to say I is the unit vector in x direction, j is the unit vector in j direction, which means if you travel by 1 unit, you will in x direction, you will be at 1i. If you travel by 1 unit in j direction, you will be 1j. So this vector is nothing but 1, 0, and this vector is nothing but 0, 1. So that is the representation of the unit vector I and unit vector j. And if you write or if you show any point in x and y plane, that can be written as a linear combination of these two unit vectors. So as long as that point is in the span means the space occupied by these imaginary vectors, as long as that point is in the span or the column space of this unit vectors, that point is contained in the plane. So what it means, if I have a point 3, 4, so this clearly is a point that I can write something like this: 3, 1, 0, because this is the unit vector I, plus 4, 0, 1, because this is the unit vector j, and this point 3, 4, if you think about the column space, is in the column space of the matrix 1, 0, 0, 1. Now, it is interesting to point out at this point that this first vector is orthogonal to the second vector, which means if I were to take, say, v1, v2, and if I were to take v1 times v2, which is nothing but the dot product. If you think about the dot product is a dot b is equal to a b cosine of theta, is written as v1 multiplied by v2 transpose, which means 1, actually this is written as v1 transpose so if you look at the dot product of these two vectors is 0, and the dot product can only be 0 when theta is equal to 90 degrees. And that means that these two vectors are perpendicular to each other. Now, that means these two vectors, and if you were to look at the determinant, so if you look at the determinant, one, 0, 0, 1 is 1. If you were to find out the amplitude or the magnitude of the first vector, square of 1 plus square of 0, square root 1, square of 0, square of 1, square root 1. So the magnitude is 1. So this vector space is orthonormal. Space is orthonormal. So this is an important concept. So if you want to express the location of any point in the space, essentially what you would do is you will take these two orthonormal vectors, or you would take the column space and multiply by some scalar constants. So if I were to say, let me give you a point, say 1, 2, and 3. As you can see, this is the x coordinate, this is the y coordinate, and this is the z coordinate, but the plane only consists of x and y coordinates. There is no z. So since there is no z, this point does not fall on x, y plane. So that is an important concept. So in other words, we can only find the solution, or we can only draw the point as long as that point is within the column space of this matrix. So to write this problem in words, if I have AX is equal to B, where A is a matrix, known matrix, B is the known vector, we can find S. X can only be found if B is in the column space of A. If B is not in the column space of A, then it cannot be found out. In other words, you cannot draw a point in 3 dimension on a plane which just has 2 dimensions. Now, column space is denoted as C of A. So this is the notation for the column space. And I just want to mention a couple of properties of the column spaces. So the column space would include the zero vector, so which is 0, 0, 0 transpose. It includes all the line, a line of all the vectors x1, a1, plane of all vectors x1, a1 plus x2, a2, and the complete 3-dimensional space, assuming A is a 3-dimensional matrix with all vectors x1, a1 plus x2, a2 plus x3, a3. And again, we specify that the vectors a1, a2, and a3 should be independent. Should be independent. What do I mean by independent? Which means x3 should not be written as some sort of linear combination, or a3 cannot be written as, so a3 is not equal to some linear combination gamma 1 times a1 plus gamma 2 times a2. So there is some non-zero constant a gamma 1 and gamma 2, and third vector is not a linear combination of the first two vectors. Now, the next important concept is how do we find out um, the basis? And just to recap, in the last lesson or last slide, we said we try to express this entire plane using two basis vectors. So this is, so I and J are nothing but basis vectors. So how do we establish the basis vectors? And the basis is nothing but the subspace of full set of independent vectors. So basis vectors are nothing but a subspace that comprises of a full set of independent vectors. So if you think about XY plane, any point in XY plane can be written as a combination of I and J. Now, what it means is, let me take a very simple example. How do we find out a basis vector? So the finding a basis vector is quite straightforward. So if you have a matrix, something like this, this matrix is 1, 3, 8, 1, 2, 6, 0, 1, 2. So if you have a matrix, something like this, now you can see very clearly that this last column is not independent. Why it is not independent? Because if you look at this first column, C1, if you look at the second column, which is C2, if I were to do 2 times C1 plus 2 times C2, I get C3. So in other words, the third column can be written as a combination of first two columns. So what I'm going to do is to find the basis, or to find the column space. What I'm going to do is I'm going to first take the first column 1, 1, 0, second column 3, 2, 1, and then start. So what this means is this matrix is an n by n matrix. It is 3 times 3. So you have n, which is the dimension of this matrix, as 3. But the number of basis vectors is 2. And this is nothing but also called as the rank. Now let's extend this concept to another matrix. If we have 1, 0, 0, 2, 4, 0, 3, 5, 6. And you can see C3 cannot be represented as some combination of the first and the second column. So in this case, all these columns form the column space. C is equal to A. So N is equal to 3, R is equal to 3. So N, size of the matrix, is equal to the rank of the matrix. The last example is if I have something like 1, 1, 1, 2, 2, 2, 5, 5, 5. As you can see, the second column is nothing but 2 times the first column. So C2 is equal to 2 times C1. The third column, 5 times C1. That means my column space is just going to be 1, 1, 1. So N is equal to 3, rank is equal to 1. So what we did is in this problem, we are trying to decompose. So we found the column space. What I want to do here is I want to write this as its matrix factorization, column space multiplied by the rows. So A is the matrix. So in this particular case, A has dimensions 3 by 3. This is 3 rows, 2 columns. So this factorization, this multiplication to be valid should be 2 times 3. Only then this factorization would make sense. And some of you may ask me how to perform this factorization. And the way you can do this, the easiest way you can do this is by using MATLAB or some other numerical solution, numerical technique. So let's try to do this factorization for one simple problem. So assume the same matrix. If I have A is equal to 1, 1, 0, 3, 2, 1, 8, 6, 2. My column space, this matrix, I'm going to write that as a column space 1, 1, 0, 3, 2, 1. And I need to find another matrix that would give me this factorization. And you can see it's not difficult to visualize. This is 1, 0, 0, 1, 2, 2. So if you were to multiply 1, 3 by 1, 2, 1, 0, you get this. If you multiply 1, 3 by 0, 1, you get 3. If you multiply 1, 3 by 2, 2, you get 8. So this is the factorization. It is important to note that number of columns is equal to 2. That is same as number of rows. And this is the fundamental theorem in linear algebra, which states the number of independent columns is equal to number of independent rows. And this is a very fundamental concept in linear algebra. And if you want to find out R, the MATLAB command for this is R E F A. This is also called as row reduce. Echelon form. And this is called as the column space C, and this is called as the row space R.